So on to our next example. The instructions are pretty much the same. It says factor each binomial completely. If the binomial is prime, say so. So in this example, we're going to run into some polynomials that we actually can't factor, but you might think you can factor them if you're not paying attention. So in part A, we're given the polynomial 16y squared plus 25. Now this looks very tempting. It looks like this might be a difference of squares because the 16y squared we know is a perfect square, right? The square root is 4y. And the 25 we know is a perfect square. The square root of 25 is 5. But the problem is the sign in the middle. This is a plus. We don't have a difference. So that means the polynomial is prime. It's not factorable. Okay? Even if you have two perfect squares, if the sign in the middle is not subtraction, the polynomial cannot be factored. Okay, so we would call this polynomial prime. So it is a fact that if you have the sum of two squares, the polynomial is prime. Okay, but sometimes students think that you can factor this by changing the signs in the difference of squares formula. Okay, so for example, 16y squared minus 25, we know by the difference of squares formula is equal to 4y minus 5 times 4y plus 5. All right, so sometimes students think that 16y squared plus 25, where the sign in the middle is addition, should equal 4y plus 5 times 4y plus 5. Is this true? Does this make sense? Well, if you multiply out 4y plus 5 times 4y plus 5, do you get 16y squared plus 25 back? Well, try it. 4y times 4y is going to be 16y squared. 4y times 5 is going to be plus 20y. 4y times 5 again is going to be plus 20y again. And then 5 times 5 is going to be plus 25. So you notice in the middle here you end up with 40 y's. So altogether this product is equal to 16y squared plus 40y plus 25, which is not the same thing as this. Okay, so this is not true. Right? So you cannot just tweak with the signs to factor a sum of two squares. Okay, a sum of two squares will always be prime. So look out for that.